Hey, so hopefully you guys have been able to successfully do assignment number 1. Am I right? No problems? Okay. So we do have teaching assistants for of our course. So just in case, for whatever reason, the code was not working or the setup is not correct, I'll put the information about the TAs on our CPG 586 Kiwi website. Okay, so hopefully you guys all remember http://kiwi.bridgeport.edu/CPG 586, right? And the username password were UB student. And did I change it or did I leave it? I forgot now. What was it? UB student. Okay, I know for one of them I had changed to 2022. So, okay, so go ahead and unmute and you can ask me a question about the assignment. What was the question?
Sir, good morning, sir.
Mm-hmm.
Why didn't we use the activation function in the code in the assignment one, sir?
Sure, I will clarify that as we go along today.
Okay, sir. I have other two questions. We are expecting to have ones and zeros as outputs, but we got decimals in the output.
Yes, so to clarify that part, see, we had a single neuron in the first assignment, right?
Yes.
So anyway, the output will be numbers, like decimal numbers, as you pointed out. So the way we're training it is, if I remember correctly, the equation of the line was 2x plus 0.3, something like this. Right? Okay. I can double check the assignment, but if that was the equation of the line, so whatever that line is, if the point is above the line or below the line, we were classifying it as 0 or 1, right? But neural networks do not produce exact 0 or exact 1. So the way we were doing it is to see what is the decision from the neural network. If the output is greater than 0.5, we were assuming the given point is above the line. If it is less than 0.5, the given point is below the line. Did that clarify the question?
Yes, sir. I did try to use this condition in the output, and
Okay. All right. So hopefully as we go along further today and some of these issues will get further clarified. Okay. So for those of you who are attending in person, let me point to you guys, Musleh over here, Musleh. Musleh is our PhD student and doing his work in AI, a very brilliant student. In case you have any issue with any of the questions in coding, implementation issues, Musleh will set up some office hours in AI lab as well, so you can stop by. And we have a few other TAs, and I'll put their information on the website, okay? So you guys will have a lot of excellent help as we go along, right?
Hello,
Hey,
sir.
yes.
Hi, sir. I just need to know that this assignment one deadline is due date is today, right? At
Yeah.
11 p.m., right?
Mm-hmm.
Yeah. Okay.
Yeah.
Thank you, sir.
Yeah. So for assignment number 1, Musleh, if you can extend it to 2-3 days more, so that just in case some people are still having some issue with setup, if you can make it maybe Thursday evening. So yeah, we'll extend the assignment 1 deadline to a few more days, but make sure that from now onwards, try to abide by the deadline. Okay. All
Sure,
right.
sir.
Was there a question?
No, sir.
Okay. All right. So, okay. So now let's come to our learning. Okay. So our first goal is we want to know how do neurons learn? Okay, and last time we answered what exactly is a neuron. Okay, neuron is a very easy computation. We discussed that every neuron has a summing unit. Okay, every neuron takes some inputs. Okay, for example, x0, x1, xn. So it could be n could be 9, so that total there are 10 inputs, right? Every neuron will multiply each input by what we call a weight, which is just a number. Okay, so for example, Wn. Every neuron has one additional input where the input is always 1. It multiplies it by what we call a bias. Okay, so after multiplying all of the inputs by W's and then adding the bias to it. So for example, if we call this output A, then the equation for A, as you can see, will be W0 times X0 plus W1 times X1, right? Plus keep going up to Wn times Xn. Whether I write Xn first or Wn first doesn't matter. And plus 1 times B, which is just B, right? So if the reason I'm calling A is this is what I call the actual output. So I use my own terminology as A to indicate this is the output being produced. And depending upon the inputs, depending upon the value of the weights, this A could be 2.3, it could be negative 0.8. So it will be some number, right? Okay, so then what we do is we pass it through an activation function, and then we produce the output. So, sorry, actually in my terminology, I made one mistake. In my terminology, I call this S as the sum. Once we pass it through the activation function, then I call it A. So S will be W0 times X0, right? And A will be the function applied to S, so f of S, so whatever that activation function is. So this is what I call the actual output. S is the sum. Okay, so how do neurons learn? Okay, so we need, so there's 2 classes in AI, supervised learning. And there's another category that you guys will learn later on, which is unsupervised learning. Okay, in supervised learning, we need training data. So somebody has to tell us for a given input, what do we expect the output to be? Okay, in this training data, there will be some X given and some Y given. So again, whether we use the term Y or not, a popular choice is X for the inputs. Okay, and again, it doesn't mean X is one number. It could be 10 numbers as an example, right? Y could be one number, Y could be 10 numbers, depending upon how many outputs are being produced by our neural network. So Y is what we call the target, or sometimes, people call it the expected output. So this is coming from the training data. So both X and Y are coming from the training data. Okay, so this will be given to us. So let's, for a single neuron, let's pretend the Y is just one number. Okay, so now we pass the Y and A to a loss function. Okay, loss function, as we discussed in the previous lecture, will always produce one number. Doesn't matter how complicated our neural network is, this will be a single number, right? So this loss tells us that the actual output, how close it to the expected output. If there's a big difference, that means the neural network is not doing a good job. We want the actual output to be very, very close to the expected output. And like I said, in supervised learning, somebody will give us what is the input and correspondingly what is the expected output. Okay. So then what we do is, if it is quite a bit different from the loss, so there is a forward pass. Okay, so we'll take this training data, this X, we'll feed it through our neural network. So we call it the forward pass. Okay, so once we go multiply by the weights, whatever the training input is, compute the actual output, then based on from the training data, whatever was the target, based on the loss function, we compute the loss. Then what we do is we go backwards. And as we go backwards, we adjust the weights so that next time, the difference between the actual output and the expected output reduces. Okay. So as we go along, you guys will learn a lot of different types of loss functions. A popular loss function would be, for example, a mean squared error. So one example of a loss function is, we call it mean squared error, or we abbreviate it as MSE. Okay, so it could be as simple as subtract the 2 and take the square. Okay, so why do we take the square? Why not just simply say, give us the difference between the actual output and the expected output? Anybody wants to comment? Why do we take the square? What's that? No,
To cancel out the mean
no,
when
that's
we are differentiating it.
No, so let me give you the answer, right? So suppose I'll give you an analogy. You are driving, you go to a new city, okay? And let's say you don't have the GPS, okay? And somebody tells you, oh, you know, there's a 20-story building and you can see it from anywhere. So suppose there's a big building over here and there are a lot of roads over here. And somebody tells you, okay, you need to come, our office is within 50 yards of this building, right? So what will you do as you're driving? If you don't have the GPS, you'll start to see, okay, am I getting close or am I getting away from the building, right? So gradually you'll get there. So let's say at some point in time, you are half a mile away from the building, okay? So let's call it plus 0.5. Okay, your loss is 0.5, right? Is our goal to increase this distance or decrease it to get closer to the building, right? So we have to decrease it. So same in neural network, the goal is to reduce this loss so that we get close to our target, okay? When you're driving, you want to get closer to the taller building because somebody told you the destination is close to this building, right? Okay, so suppose now instead of being on the right side of the building, you are somewhere on the left side of the building, okay? And let's say if you are here, you're roughly still close to point, or maybe, you know, let's say, remember in x-axis, if this is your goal to get close to the y-axis, okay? So if you're in the x direction, in this side, we indicate it's positive. On this side, we indicate it's negative. So if you are somewhere over here, you are negative 0.6 away, right? But when we take a look at the loss, we are interested in how far away from it we want to eliminate positive or negative. Okay, so what happens if we square it? Okay, if we square a negative number, what happens? It becomes positive number. So basically, this gives us an idea of the magnitude, how far away we are from our target, regardless of plus or minus. So that's why typically we will use the loss function as a square function. Okay, in very, very special situations, if the sign is important, you can leave it as y minus a and not worry about it. But like I said, majority of the problems will go take a look at the square of the error, right? But there are other loss functions that we gradually will discover. Okay, so anyway, goal is once again to reduce this loss. Okay, so now the question is, for a neural network, how do we know how to minimize this loss? Okay, and as we talked about in math, okay, easy way, if you're given some complicated equation, so you are given some f of x equal to, let's say, 2x squared minus 3x plus 4 times sine of x minus 3 times e to the minus x, right? So this is some complicated equation. Let's say if I draw it like this, this is what as a function of x, this is what f of x looks like, okay? So you start plugging in the value of x, you compute it, this is what we plotted, right? Okay, so our goal was, let's pretend which value of x will give us the minimum f of x. Like, where is it minimum, okay? So for example, in this picture, let's pretend this is the minimum point, okay? So in math, what we do is we compute the derivative. We talked about, the derivative is the slope. So for example, if we are here, the slope is a negative. So we start to move over here, right? So hopefully the idea is at each time we move, we'll take a look at the slope and such that eventually we can come over here, okay? If the function is very complicated, let's say sometimes it goes up, then it goes down, then it goes up, then goes down, right? Then if we simply take, for example, d of f of x over d of x and set it equal to 0, which is the standard technique in math to find out what is the value of x at which the function has the minimum value, okay? It will work for a smooth function like this, like a parabola. It will give you exact value if you calculate it like this, at what point it is the least value, right? But if the function is, like I said, complicated, going up and down, okay, then there is no closed form solution, okay? Meaning you cannot simply take the derivative and set it to 0, because then, if you started over here, it will just say, this is the answer. But in reality, the answer is over here. And, sometimes you have to go up, you have to go down, right? So a lot of research have gone into how do we find the minimum value of a complicated function, right? So remember this, think of it this way, our loss is a function. Okay, a function of the inputs, function of the weights. Okay, so we want to find out what is the ideal weights that we will set over here. This is what we will be controlling, W0, W1, Wn, and B. Okay, input data we do not control. Somebody says for this input, this is the target. Okay. When we design a neural network, it's the weights and the biases that we determine, which will give this a very, very close to the target, not just for one set of data, but for all sets of training data, all sets of unknown data. So that is the overall goal of designing a neural network, okay? So these weights and biases, okay, these are referred to as parameters of the network. And typically we'll start these randomly because we don't know what is their ideal value. So we will initialize them at some random numbers. And gradually through the training data, like I said, we'll go forward. Then compute the loss. Then we'll go backwards, adjust these weights, and we will repeat it many, many times so that for majority of the training data, the actual output produced is very close to the target output. So that is at a high level goal for all neural networks, regardless we have one neuron or million or billions of neurons, okay? So like I said, for a single neuron, we could come up with a closed form solution, meaning it could give us the ideal values for the weights. Okay, but as soon as we start putting more and more neurons, what happens is the loss function becomes more and more complicated, you know, so that we cannot easily determine what is the ideal value of the weights that will give us the lowest loss for majority of the training data and will work well for the unknown data, right? Okay, so this is where a lot of research went into finding out how do we determine how to optimize the parameters of a network. In other words, how will this neural network learn? Okay, so as of now, the best algorithm, it's an iterative algorithm, meaning it won't give us the answer right away. We have to repeat this process many, many times. And that algorithm, which we use for the optimization of a neural network or the learning of a neural network, is called the gradient descent algorithm. Okay, and gradient is another word for the slope, or another word for the derivative. Okay, like, you know, if you are, for example, given 2x cubed minus 3x squared plus 7x, right? So remember from your basic math, the dy over dx is what we call the gradient or the slope or the derivative, okay? And you will remember it's pretty easy to calculate. You bring the power down. So 3 will get multiplied by 2. And then you reduce the power. So it will become 6x squared minus, again, you'll bring 2 down. 2 times 3 is 6. And it will become x raised power 1, which is 6x, plus 7x. You can think of as x raised power 1. So you bring 1 down, will become 7, and anything raised power 0 is 1. So this is your answer as an example, okay? So we'll apply the gradient descent algorithm. And so the question is, for a single neuron, like I said, it's not as complicated, but the minute we start putting more and more neurons, then the calculation of the gradient to apply or in the form of the gradient descent algorithm becomes a little more involved, right? So then some years ago, somebody came up with a clever way to break down this complex problem if there are many, many neurons, so that we can make it as easy as possible. So the general philosophy is like this. See, if I give you an equation of a line, right? So let's say at x equal to 3, let's say y is 4. So this is my y-axis, this is my x-axis, okay? And let's say I'm given one more point. Let's say x of 5. And let me pretend this is 6, right? So what is the dy over dx? Okay, remember this is basically saying change in y over change in x. That's what the derivative is. That's what the slope is, right? So what is the change in y between these 2 points? 6 minus 4. If I pick this as the starting point, y is 6, right? The second point is 4, right? Same way for the same 2 points, what is the change in? So for the first point, it is 5. Change in the second point, x is 3. So you can see what is the slope then? 2 over 2 equal to 1. So the gradient is 1 over here, right? Okay. So what we will do is to apply the gradient descent algorithm to a complex network with many, many neurons. So if we have a complex neural network, okay, like I said, to make this gradient calculations very easy, what we will do is pretend there are some neurons over here. We feed in some input x. Remember, it multiplies by some weights, right? And then it produces some output. Okay, suppose I call this output P. Then it goes through, let's say, another set of neurons, multiplies by another set of weights, and let's say it produces the output Q. Okay, then let me pretend goes through another set of neural networks or some neurons, multiplies them with different, right? And suppose it produces the output, let's say, R. Okay. Okay, so let's pretend our goal was to, let me call this W1, W2, W3. Okay, so the weights over here are W1, weights over here, second box is W2, W3, right? And let's pretend what to implement the gradient descent algorithm, our goal was to find dr over dw1. Okay, now in math, we use the letter d to indicate the derivative. There's also we write it like this, which is called the partial derivative. And let me quickly refresh your memory. What is the partial derivative? Okay, suppose I give you an equation, y equal to 3x squared minus 4x plus 5z squared minus w. Okay, so pretend this y is a function of x, w, and z. Okay, meaning there are 3 variables involved. Together, they produce some output, which we're calling y in our example. Okay. So rather than see, because there are 3 different variables involved, so now what we will do is we will use partial. We'll say, how is y changing with respect to x? Or how is y changing with respect to z? Or how is it y changing with respect to w, right? So when we compute the partial derivative, we will say like this, partial y over partial x, meaning change in y over change in only x, not w, not z. So all the others like z and w are treated as constants, meaning we zero them out. So if you just focus on x and zero out the z and w, what will happen? Remember, we bring this power down over here. This will become 6x and minus 4, right? Same way, what if I say partial y over partial z? How is y changing with respect to z? So now what will we do? Make x and w zeros and only focus on the z term. So z term is 5z squared, so that will become 10z, right? Similarly, you get the idea. What if I say partial y over partial w? Can anybody tell me what will that be? Okay, there's a single w term. And
-1.
minus 1. Okay. So, so when we create neural networks, because think of this W1, W2, W3 as 3 variables, just like I had X, W, and Z. Okay. So we are interested in how the output is changing with respect to W1, how the output is changing with respect to W2, and so on. So we do partial derivatives. Okay. So let's pretend our goal was to determine not dr over dw1, because now there are multiple weight variables involved, right? So this does not make sense. So we'll be interested in how is r changing with respect to w1. Okay. So as we draw and put the real neurons over here, you'll see it will appear fairly complex. But as you guys have learned in many computer science, math, engineering courses, if you are given a complex problem, easy way to solve it, break it into simpler sequence of simpler problems. So same thing we will do over here. What we will do over here is we'll break it into partial r over C. Q is feeding to this network and producing R. So you will say, let's compute partial R over partial Q first. Okay. Then let's go over here to the previous one. Partial Q over partial P. Okay. And then let's now, because our goal is to find the change of R with respect to W1. Now we will say, okay, let's do partial R over partial W1. See if this makes sense. Last one, because our goal was to determine only up to W1. Oh, sorry, partial P. Yes, yes, thank you. Yeah, I made a mistake. So it will be partial P with respect to W1, right? So remember, the derivative is change in Y over change in X. If I gave you something like 5 divided by 3 times 3 divided by 7 times 7 by 6, what will be the answer? So remember, these cancel, these cancel. The answer is easy, 5 over 6. So, because derivative is nothing, regardless it's a partial derivative or not. It is like one thing divided by the other. Change in this divided by change in this, right? So can I cancel this? Can I cancel this? So what's the right-hand side? Partial R over partial W1, right? So as you will see, it's a lot easier to calculate just the derivative in one small step. So by breaking it into smaller problems, our whole problem will become a lot easier to solve, right? So let me show it to you. So now let's go to first a single neuron, then 3 neurons, then 5 neurons. And in your second assignment, you'll be programming the 3 neuron and the 5 neuron, and you'll be calculating the derivatives and seeing it's able to learn, right? Okay, so first let's go to 1 neuron, which you already did, but let me quickly refresh your memory based on our new knowledge to see this will make sense, okay? So we will assume there are 2 inputs, X0 and X1. There are 2 weights, W0, W1, and the bias. Here's some, right? Activation function, here's A. And let's pretend we are given some target Y. Okay, through the training data, we have a loss function and we are given L. Okay, and the loss function we will be assuming is A minus or Y minus A squared. Okay, and remember when we take the derivative, we bring this 2 down. Okay, so to make our calculations easier, I'll assume the loss function is 0.5 y minus a squared, so that once we do the derivative, it becomes, we're not having too many decimal things going around, right? Okay, so 2 and 0.5 will give us 1. Okay, so this is our loss function, right? So remember, our goal is to determine optimal values of W0, W1, and B that produce the lowest loss, because we want to decrease the loss. Okay. So in other words, to determine this, what we need to do is we need to determine partial L over partial W0. We need to determine partial L over partial W1, partial L over partial B. Then we will set these to 0 and apply these in a iterative manner using the gradient descent algorithm, and gradually will tell us what is the ideal value for W0, W1, and B. Okay, so now let's see if we can calculate this. As I mentioned, our learning process is a two-step process. We go forward. Okay, then we go backwards. And when we go backwards, that's when we will adjust the weights and biases. Okay. Okay, so let's write the forward equations first, starting from the inputs. Okay, so what is the equation for S then? W0 x0, correct? Multiply these two plus W1 times x1, correct? Plus 1 times B, which is B. Okay. Now, activation function. So this is our activation function. Okay, in the beginning, like I said, I'll assume this to be just a linear function, meaning it doesn't do anything. Whatever the input is, it just passes straight through. So if I plot the activation functions, you can think of it, it's like a straight line. If the input is 1, output is 1. Input is 2, output is 2. So it has a slope of 1, or the derivative of the activation function with respect to the input is 1. Like complete. So input is -1, output is -1. So it doesn't do anything, right? So we're assuming in the technical terminology, a linear activation function. Okay, then we will change it to something else. And why do we change it? I'll explain that as we go along. Okay, so anyway, we have this, right? Because if the input is 2, output will be 2, meaning if S is 2, A will be 2. If S is 3, A will be 3, right? Because it's a linear activation function, so you can see the equation for A is same as S. Okay, now let's go to the loss. Loss is 0.5 y minus A squared, right? Okay, so we have to determine partial L over partial W0. Okay, so let's see if we can do that. So can you take a look at this equation, partial S over partial W0, and tell me how will we compute this, right? So if you take a look, let me use a different color. So we want to calculate partial L over partial W0, right? So like I said, if we break it into multi-step problem from L, let's go to A. From A, let's go to S. From S, let's go to W0, just like I showed you before, right? So partial L Okay, partial L over partial W0. Let's follow this blue path over here. What would this be? Partial L over partial A, correct? Then multiplied by partial A over partial S. And then lastly, partial S over W0. Okay, so now you will see all of this is extremely easy to calculate. Let's go to the first function, first part, partial L over partial A. If L is 0.5 y minus a square, then from here you can see partial L over partial A. You will bring 2 down over here. 2 and 0.5 will become 1, right? You will leave this as is. Then further, whatever the inside is, you have to take the derivative of the inside with respect to A. So with respect to A, it's -1. So the answer, as you will see, will become minus y minus A. Okay, if you have not done calculus before, for the time being, because the loss function will most of the time will be like this. Even if you memorized it, okay, this is what the answer is, it will be good enough for our development, okay? So partial L over partial A, like I said, is minus y minus A, correct? Okay, so now let's go to the partial A over partial S, the second part over here. What is A? S. So what will be partial A divided by? This will be 1. Okay, because see, you can think of it like 1 over here. You'll bring 1 down and any S will become 0. So anything raised power 0 is 1. So partial A over partial S is 1. Okay, what about the third term? Okay, now go to this equation for S. And like I said, only the W0 term will be kept. All others will be treated as zeros. Okay, so what is the change in S with respect to change in W0? It's just so think of this x0 as like a constant. So this will be simply x0. Okay, so if I multiply this, this will become minus y minus a multiplied by x0. Okay, there was a question. Okay, okay, the question was I discussed dB0, dW0. Okay, okay, how should I answer that? Okay, so we are going into more detail in this lecture. So yes, last time's lecture was a little bit of an overview of things. So see if this one makes more sense to you, okay? But try to follow this development, okay? So anyway, partial S over partial W0, as you can see, will simply be x0, right? So partial L over partial W0 will simply become this equation over here, right? Okay, very similarly, what if we wanted partial L over partial W1, okay? So again, what we'll do is start from here. You can write it like, again, partial L over partial W1 multiplied by partial A over partial S multiplied by partial S over partial W1, right? Okay, so this one we already, partial L, what did I do? This should be partial L over, sorry, I made a mistake. This should be partial L over partial A. So this one we already calculated is minus y minus A, correct? Then partial A over partial S, as we discussed, it's a linear function. So this is 1. And then partial S over partial W1, only now this term will be considered. Everything else will be 0. So what will this part be? X1. Okay, so this is the answer for partial L over partial W1. Okay, similarly, the third thing we wanted to calculate was partial L over partial B. So if we go to partial L over partial B, again, you can think of, we go from, let me use another color. We go from L to A to S, now S to B, right? Okay, so this will be, as you can see, partial L over partial A over partial S, and partial S over partial B. So partial L over partial A, we already did it, minus y minus A, correct? Partial A over S, 1, S over B. So go to this term over here now, and only B will be treated as a variable. All others will be constant, meaning if they don't change. Their effect to their contribution to the partial will be 0. So think of it as if we have S equal to B. Okay. So then what is change in S with respect to change in B? 1. So this is so now that we have 3 partials calculated, right? So now let's come to the gradient descent algorithm. So for the gradient descent algorithm, okay, instead of focusing on W0, W1, and B, okay, the general idea was, for example, if we take a look at the loss function, right? Y minus A square 0.5, okay? So if we plot the loss, because remember, we are computing how is W0 changing with respect to L, or how is W1 changing with respect to loss, right? So suppose I have a general, instead of saying W0, W1, I just say W, okay? Then if you take a look at the loss is like a parabola. If we plot it out, it's parabola, right? So we want to know this is at this point, the loss is the lowest, so this is our goal. Find out which W produces the lowest loss. Okay, so like I said, we start out randomly with initializing. If we initialize over here, then the slope over here is negative. If you draw the tangent, if you started W over here, the slope over here is positive, okay? So the gradient descent algorithm says each W should be adjusted as minus W partial L over partial W. So this is the gradient descent algorithm. Okay, and intuitively, it makes perfect sense. As I mentioned, for example, over here, slope is negative, right? So if the initial weight was over here, okay, as you can see, to get to the lowest loss, we have to increase the weight, okay? So if the slope is negative, right, you can see this is negative term. Negative, negative will become positive, which means the next value of W will take the old value of W and will add something to it because this negative and this negative is becoming positive. So next W will move over here. So this will be the W next. So you can see gradually it will move. And we will repeat this process many, many times until we see it's not improving. So then we have gotten close to the Okay, so same thing, so what I'm trying to say is, if we plot with respect to W0 or with respect to W1 or with respect to B, okay, in our simple single neuron case, the loss will turn out to be a parabola, okay? And like I said, as we apply repeatedly these type of updates, then whatever the final value of W or B becomes, that will be the ideal that reduces the loss to the lowest, okay? So intuitively, like I said, that's the idea. Because we are randomly initializing the weights, if you started the random value too high, it will start to decrease it, because over here, the slope is positive. And if this value is positive, then we are subtracting something from the original, which means we are moving the weight in this direction. And vice versa, if we start over here, we are moving it in this direction, okay? From learning point of view, like I said, as we set up the network, we decide how many parameters we need to learn. In a single neuron with 2 inputs, there will be 2 weights and 1 bias. So we will need to calculate the 3 partial derivatives of the loss with respect to each one of the parameters and repeatedly apply these calculations, okay? So now let's make it a little more complex. Let's put 3 neurons in it and see, can we learn from 3 neurons? As you will see, the equations will become a little more complicated. So let's draw 3 neurons. Okay. Some. And then gradually I'll change the activation function. And let me assume 2 inputs, x0, x1. Okay, as we discussed, every input goes to every neuron. And let me call it W0, W1, W2, W3. Let me call this W4, W5, and let's call it B2. Okay, let me call this S0, A0, S1, A1, S2, A2. And suppose this is our target Y, which is given to us. This is our loss, L, and let's assume the same Y minus A squared. Okay, so how many learnable parameters do we have? Remember, the weights and biases are the learnable parameters, which is what we need the training data for it, so that we can optimally determine what is the ideal value of those weights, so that the loss will become as less as possible for the given set of training inputs and the corresponding expected output, okay? So how many unknowns do we have? Learnable unknowns, W0. W4, W5, right? And B0, B1, B2. So how many that comes out to be? 9, right? So you can start to see that for even a 3 neuron network, now we have to do 9 derivatives, okay? And easily, what if we have millions of neurons? How? Okay, so we'll develop a very, very good, easy strategy so that it doesn't matter gradually whether we have million neurons or billion neurons, it will work, right? Okay, so let's go one step at a time. Like I said, the goal is, even if it is a complex problem, break it into very, very simple set of steps, okay? So let's write the forward pass. So in the forward pass, can you tell me what will S0 be? So W0 X0 plus B0, correct? Okay, what about S1? Okay, see, if you take a look at S1, X0 is being multiplied by W2, right? So W2 X0 plus, take a look at W3, it's coming from X1 plus B1, right? Next equation is A0. How is A0 related to S0? Again, let's assume linear activation function. S1 equal to A1, correct? What about S2? S2, see, the input to the second neuron is coming from A0, which is being multiplied by W4. So W4 A0 plus, similarly, A1, as you can see, is being multiplied with W5 plus B2, right? And now how is A2 related to S2? So if we assume linear activation function, it's the same, right? And lastly, the loss we already have over here. Okay, so to implement the gradient descent algorithm, we will need 9 partial derivatives, right? We will need partial L over partial W0, partial L over partial W1, and so on, and partial L over partial B2, okay? So because we have the forward equations, we can easily calculate all of these partials, right? So let's take a look at partial L over partial W0, which is the most complex one. Okay, so see, L loss is over here, right? And where's W0? All the way towards the input. So like I said, you'll keep going back one step at a time, right? So let me use the blue color to show you how will we go back. So from L, we'll go back to A2, then A2 to S2. Okay, which way is W0? W0, you can see, is in this path over here, the top path over here, right? So S2 to A0, and then A0 to S0, then S0 to. So this will be your strategy. In the beginning, if you draw it out, because if you try to do it in your head, everybody will make a mistake. But if you draw it very nicely, you'll never make a mistake. So now it's easy. Okay, so let's express this as a multiplication of all these partials. So you can see, first we will go partial L over partial A2, correct? Then partial A2 over partial S2, partial S2 over partial A0, correct? Then A0 to S0, then partial S0 to partial W0. Good. Okay, so now we can very quickly write all of these. What's partial L over partial A2? Okay, so this, let me make it A2 over here, because the A2 is what's operating on the final loss. So what's partial L over partial A2? 2 comes over here. So you can see minus. Everybody agrees? What's partial A2 over S2? See A2, S2R. So this will be 1. S2 over A0. Go to the S2 equation. S2 over. Remember, everything other than A0 will be treated as a constant. So what's the coefficient of A0? Just W4. See, you can think of it this way. See, if I gave you y equal to 2.5x, what is dy over dx? 2.5, right? So think of it this way. When I say S2 over A0, remember W4 is a number. It was initialized randomly. Could be 2.4 or 2.5 as an example. So that's why partial S2 over partial A0 is simply W4, okay? How about next one, A0 over S0? This is the relationship between A0 and S0, so which is 1. And lastly, did I do all of them? S2, A0, A0, S, okay, S0 over W0. So go to the first equation with respect to W0. And again, input is like a number, okay? But now we are interested in W0 becomes a variable because our goal is to find how, if W changes, S0 will change. So that's why this will be X0, right? So did we find this? Okay, let me do one example for you. Rest I will leave for you as a exercise. You'll go home and try it yourself. Okay, suppose we wanted to figure out, let's say, partial L over partial W5. Okay, so what will this be? So this will be partial L over. So from L, we'll go to A2. A2 to S2, very good. And S2 to. And we are done because we stopped. This is where we wanted to, right? So partial L over partial A2 is minus y minus A2. A2 over S2 is 1. And what about S2 with respect to W5? So go to the equation for S2. Okay, with respect to W5. So it's simply A1, right? So can we calculate all these 9 partial derivatives? Easy, okay? I mean, it will take some time, but we can do it, right? So then how will the learning algorithm look like? Our general, our learning code will look something like this. Compute the forward pass. The forward pass, okay, will basically be these 6 equations. So in Python, exactly like I'm writing, you will write these 6 equations. Here are the 3, here are the 3. So it's 6 equations as your forward pass, right? Then you will write the, remember all of these partial L over partial W0, you can create a variable in your code. You can call it, for example, DW0, because it's always assumed that the top is always with respect to loss, right? So in Python, you can say DW0, and this will be the code you will write in Python as an example, right? So same way, this part over here was calculating partial L over partial W5. So you can have dW5, whatever this is, right? So once you have all of these, D0, dW0 up to dW6, then dB0 up to dB2, right? There were 3 biases. Okay, then you will remember our gradient descent algorithm is W0 will become W0 minus lambda, which is the learning rate, times dW0. In Python, as an example, W1 equal to W1 minus lambda. Lambda is a learning rate which you will fix to 0.01 or 0.05 or whatever, right? dW1, and similarly up to B2 equal to B2 minus the learning rate dB2. So you will repeat this for a lot of the training data many, many times until it converges, okay? So this is whatever the final weights are, because these are the final W's and biases, those now the network has learned, so then we'll fix those, okay? So now let me introduce one more very interesting aspect of it. Okay. And the interesting aspect of it is, for example, let's say you wanted to calculate, see over here, we did like focus on this equation. We did partial L over partial W0 by multiplying all of these terms, right? Okay, what if I said calculate partial L over partial W1? How will it be different from partial L over partial W0? Okay, if I use a green path to indicate partial L over partial W1, will I go back over up to here? Will I go back up to here? Will I go back up to here? Back up to here, right? Now, instead of going to W0, where will I go to? W1. So you can see all of this path was exactly the same. These calculations were the same. So why should we be duplicating those? Why not use the result of some of the calculations to calculate the other derivatives, right? So now let me introduce a very, very important update to our gradient descent algorithm. And this is called the delta rule. Okay, so we will make our gradient descent more efficient by reusing some of the calculations. Okay, so, and the concept is very easy. Okay, so suppose I draw the same network again very quickly. Okay, so like I said, this will go over here, this will go. Okay, W0, W1, W2, W3. Then this goes over here, W4. This goes here, W5, B2, B0, B1, right? Okay, so anyway, S0, S1, S2, A2, A0, A1, and then the loss. Okay, so anyway, so the idea of the delta rule is in the middle of every neuron, we will declare this delta. So the Greek letter delta, we write it like this. Okay. So pretend right in the middle over here, I calculate some value and I'll call it delta. So I'll call it delta 2. Similarly, over here, I'll calculate something called delta 0. Similarly, I'll calculate something over here. I'll call it delta 1. So delta is basically a calculation in the middle of each neuron. So what exactly is this calculation? Okay, and the calculation is partial L over partial middle of neuron. Okay, so for example, remember I was calling this middle value as S2. Okay, so delta 2 is actually exactly equal to partial L over partial S2. Okay, similarly, can you tell me what will delta 1 be? Partial L over partial S1, because we call this S1. Okay, similarly, what will delta 0 be? Partial L over, go to S, this is S0, so partial S0. Okay, so the idea is calculate these delta values first. From these delta values, calculate all those 9 derivatives that we talked about. Okay, so step 1 will be, so we'll change our algorithm slightly. Let me go over here. Okay, so our algorithm will become calculate delta values first. Then from these delta values, calculate partial L over partial W0, partial L over partial W1, up to partial L over partial B2. Okay, so let me show you how easy would that be. Okay, let's write the forward equations quickly so that we can easily see how do we calculate these deltas. So what was the equation for S0? If you remember, this was W0 X0 plus W1 X1 plus B0. S1 was, take a look over here, X0 is being multiplied with W2. And X1 is being multiplied with W3 plus B1. And S2 was A0 with W4, right? And W5 with A1 plus B2, okay? And all the A's were same as the S's, so I won't write it, okay? Okay, so let's start with, so like I said, we'll work backwards. So first thing we will do is we'll calculate this delta 2 first. Okay, because in the backward pass, as you will see, based on this delta, we will calculate the previous and so on. it will make our calculations a lot faster. Okay, so to calculate this delta 2, as you can see, is partial L over partial S2, right? Which is partial L over partial A2, partial A2 over partial S2, and that's it, right? So what is this equal to? Minus y minus A2. You guys agree? Because see, this is 1, right? And this is partial L over partial A2, C from here to here, and then from here to S2, right? So partial L over A2 over S2. Is it clear or confusing? Good, right? Okay, so do we know delta 2? Okay, now let's go try to figure out delta 0. Okay, so delta 0. Let me use a different color. Let me see if you follow delta 0 now. Delta 0 is, by definition, partial L over partial what? S0. If we write it, won't it be, if we fully expand it, partial L over partial A2, right? From here we go to A2. A2 to S2. Then S2 to A0, very good. A0 to S0, correct? Okay, but what is this part? That's delta 2, right? So this is delta 2. So we don't have to calculate it again. We already calculated the delta 2. So if we start from delta 2, okay, what's the value of this? S2 over A0, right? So if you take a look at S2 is over here with respect to A0 is W. Okay, so think about it a little bit. As we are going from S2 to A0, what is the weight that is connecting between those two? W4, right? So you can even go over to the equation. If you do S2, partial S2 over partial A0 is W4. Or now that you have seen the pattern, you can see, oh, if I go back, whatever weight was multiplying it, that's what it will be. Okay. So in other words, this is W4, right? So once we go over here, this is 1 anyway. Okay, so what I'm trying to say is delta 0 is turning out to be delta 2 multiplied by W4. And why? Because what is connecting these two neurons? See, delta 0 is the middle of this top neuron, right? And delta 2 is the middle of this neuron. So what is connecting delta 0 neuron with delta 2 neuron? It's W4. So even if you go through the full math, you'll see, oh, because W4 is connecting, therefore the relationship between delta 0 and delta 2 is simply multiplied by the weight that connects them. Let me see if you can tell me now, without doing all the calculations, what will delta 1 be with respect to delta 1 is over here. with respect to delta 2 times W5. And you can verify it by expanding it fully and confirm that's the case, okay? So now that we have delta 1, delta 2, delta 0 all calculated, now from here we will calculate the partial derivatives, okay? So for example, if delta 2 is already calculated, right? So which is partial L over, or let's go to delta 0. So we already know delta 0, right? Which is, as I said over here, right here. Okay, so let's pretend it's known. From here, can we calculate partial L over partial W0? Okay, if I write it, won't it be partial L over partial S0 times partial S0 over partial W0? See if you agree with this conclusion. S0, S0 cancels, right? And what's the value of this? This is delta 0. So all I have to do is to find out partial L over partial W0. After I have calculated all the deltas, I just need to multiply it with partial S0 over partial W0. So if you go to the equation for S0, what is partial S0 with respect to W0? X0, okay? So all I'm saying is this is simply multiplied by X0, is this value. Okay, and you can calculate it, or pretty soon you'll see the pattern. And the pattern is, see from S0 to go over here, which is the input that is tying to W0? The input is X0. Okay, let me see if I'll give you the answer and you can go home and verify it later on. Suppose I wanted to know partial L over partial W. Let's go to W5. Okay, in terms of deltas. So W5, obviously, what comes very close to W5? Delta 2. So it has to be something multiplied by delta 2. Can you guess what that is? A1. Yes, because see, if you take a look from delta 2, W5 is, A1 is feeding to W5. So this will be simply A1. And you can confirm it, okay? So let's confirm it. Partial L over partial W5. One way to think about it is this will be from here to S2. Partial L over partial S2 times partial S2 over partial W5. And what is partial L over partial S2? What's the definition of that? Delta 2. So this is delta 2. And go to the equation for S2. Equation for S2 and find out with respect to W5, A1. And that's what we said. It's delta 2 times delta 2 times A1. Okay, so now you can see it doesn't matter how complicated the network is. You can view it and give me the answer. Okay, so let's see if you are getting good at it. Let me draw 5 neurons now. Okay, so let me do this. Let me give you a 10-minute break. Then we'll draw 5 neurons, and then I'll come to the activation functions, and we'll use an actual activation function. Hey, so before the break, we looked at the delta rule, and the idea was, it doesn't matter how many neurons we have. Okay, at some point in time, okay, so the concept behind delta rule was that it is so if there's a final loss over here, the delta value in a neuron is in the middle of the neuron, okay, before the activation function. And it's really the partial of the loss up to that point. So partial L over whatever that S is over here, that is defined as the delta, okay? So then as we work backwards, okay, for example, let's say there's a W6 over here, W7 over here, right? So for example, let's say, okay, so suppose this is delta 3, for example. Let's say there's another delta, let me call it delta 7 as an example, right? So if you've calculated some delta up to this point, then what will be delta 3 with respect to this delta? How are they related to each other? So if I call this just a simple delta, then how is this delta 3, which is up over here, how is it related to this delta? Will be multiplied by which one? W6. Okay. Similarly, delta 7, which is this over here, how will it be related to this delta? Delta times W7, right? Okay, so now let's say over here there is some input X5. This is some W9. Okay, so if you were to calculate in this example, delta L over delta W9. Sorry, not delta, partial L over partial W9. How would that be related to this delta 3? So we are interested in the loss of the partial with respect to this one. So this will be, because remember, this is very close to this neuron where we are calling the middle delta 3 in this example. So this will be delta 3 multiplied by X5, whatever the previous input is. Okay. So it makes it very easy, right? Before I show you the 5 neuron example, okay. So suppose we have some, remember the output will go to each and every neuron. So this output will go over here. This output will go over here as well, right? Suppose this is W6. Suppose this is W7 in some scenario, right? This is an activation function. Okay, suppose I call this delta 9. Suppose over here I have delta 7. Okay. And then these go further. Let's pretend to some neuron over here. And then some loss over here, okay? And let's pretend, suppose this is delta 5, okay? So now the question is, how is delta 5 related to delta 9 and delta 7? Okay, because there's, as you can see, if the bottom neuron was not there, right, then it's easy. for example, let me put a green over here. Suppose this was not there. If this is not there, then how will be delta 5 related to delta 9 in this example? It will be multiplied by
W6.
Okay, but now there's another contribution coming from this bottom neuron. So now let's put it back there. If it is there, then as you can see, the value of delta 5 will be W6 is the one which is connecting these two neurons. So it will be delta 9 times W6 plus. This delta 7 is now getting its contribution via this W7. So this will be now delta 7 times W7. Okay. So as more and more neurons come into play, you have to take a look at how many paths are leading to a particular input, and you have to accumulate all those paths. Okay. So that is the slight complication to save time. Let me show you the picture. The assignment 2 that I will be giving you very soon. If we go, I already have given you, so for a lot of these assignments, I'll provide a full solution to those. Okay. For your learning, what I will recommend is don't take a look at the solution. Do it yourself. Then take a look at the solution. Did I do it right? Or if you're totally confused, sure, you can take a look at the solution, right? Then towards the end, I will add some assignments where you are creating it by yourself. You're not getting all the solution. So anyway, if I take you to assignment 2, you will see you'll be programming the 3 neuron network. Then you'll be programming the 5 neuron network, right? We already discussed the 3 neuron network. Let's take a look at the 5 neuron example. Okay, it's already on the website under the handouts under CPG 586 Kiwi website. Okay, so picture is already there, so it's very neat and clean, so we can easily understand this. Okay, so from this picture, let's see if you can tell me. I'll ask you simple questions. Can you tell me how is delta 2 related to delta 4?
W8 into delta 4.
That's correct. W8 into delta 4 will give you the value of delta 2, right? Let's go to delta 0. How is delta 0 related to the other deltas that you see over here?
W4 into delta 2, W6 into delta 3.
Yes,
Plus.
that is correct. W4 into delta 2 plus W6 into delta 3. Okay. What if I ask you partial L over partial W7? So partial L over partial W7 in terms of deltas.
Delta 3 into W7.
If we are going up to here, right? So this will be delta 3. No, that's so let me draw it out. My question was, give me the value of partial L over partial W7. So it will be, see, if you take a look at W7, right? It's tied to delta 3 times what?
W7.
No, not W7.
No. A1.
A1. That is correct now. Okay. So let me ask you one more question. How will it be partial L over partial W2.
It's delta 1 into x0.
Delta 1 is up to over here, right? And W2 is connected to X0, so that is correct. So this will be delta 1 times X0, right? So in this example, as you can see, if we have 5 neurons, right? I have total of 10 weights and 5 biases. So you'll be writing 15 of these partial equations. Okay. If I remember correctly, as I made the solution, I might have typed one of these wrong. Okay. Okay. So, see, that's why you'll carefully do it, and you'll figure out where I made the mistake. Okay. Rather than me going fixing it, it would be a good learning for you to, see, oh, this is where I made a mistake. Okay. So anyway, like I said, the only thing the complication, the slight complication is when you have multiple paths, right? So as we discussed, to calculate delta 0, okay, it's getting a contribution from delta 2 as well as delta 3, because you'll see there's a path going over here from this neuron. There's a path going over here. Both of these will contribute to this delta 0. So for delta 2, what will we multiply it with? As you guys said a few minutes ago, W4 is the weight that connects these two neurons, right? Then if we take a look at the bottom neuron, this is delta 3. So delta 3 is being connected via W6. Okay, so once again, this is how you'll program it. And you will see that once we go to the deltas, then, so again, the general philosophy in creating the training for a multi-neural network is use the deltas because they reuse the gradients. And step 1 is always calculate all the deltas. So of course, you will do the forward pass first. You will write all the equations for what is S, S1, S2, or whatever, right? Then after that, so maybe this is step 1. Step 2 will be calculate deltas, okay? Then step 3 will be, once you have the deltas, then calculate W's and B's. Sorry, partial L over partial W's and partial L over partial B's from these deltas. Then it becomes very, very easy. Okay, so now a couple of questions related to our learning. One is, what about these activation functions? Okay, what do they do? So there are different activation functions, okay? Let me give you the motivation for activation functions. One motivation is to constrain the output. Okay, to give you an example, right? Okay, as we are going through one neuron to another neuron to another neuron, right? Okay, suppose at some point in time it produces some value, let's say 25.7. Okay, then it will get multiplied by weight, then we'll go to the second neuron, then multiplied by another weight, right? So there's a possibility this value, what if the weight is 2.3? Remember in the beginning, we initialized them randomly, right? So now it becomes close to 80 or whatever the number is. Then further, this is 3.8. So if we are using, thousands of these neurons, one after the other, it is possible the value over here becomes extremely large that will overflow in our computer, right? So that's one extreme. The other extreme is, what if the value coming out of a neuron is 0.07 and the weight happens to be 0.01, right? And similarly, the next weight is 0.02. So what happens when we keep multiplying these small values by themselves? As we go along, the values will start to become lower and lower. Eventually, at somewhere in the middle, it will become pretty close to zero, and the neural network will stop learning. Okay. So both, we don't want the value to go too high. We don't want it to go too low. So one of the goals of the activation functions is to constrain it between a certain range as it comes out of a neuron, right? So there are a couple of activation functions that we use, and gradually we'll take a look at slightly more advanced versions of these. So one popular function is called sigmoid. Okay. And the equation for the sigmoid is f of x equal to 1 over 1 plus c to the minus x. And I hinted to you in the last lecture, right? If we plot it out, what you will see is it will come out to be like this, okay? This is 1, this is 0.5, this is x, this is f of x, okay? And you can easily verify it, as we discussed in the previous lecture. If you put x equal to 0, anything raised power 0 is 1. So it will become 1 over 1 plus 1, which is exactly 0.5. Okay, if you keep x a very large value, like x equal to 100 as an example, right? E to the minus 100 is very close to 0, because e to the minus 100 is same as saying 1 over e to the 100, which is a very large number at the bottom, so which is very close to 0. So you can see if x is large, this term will become 0. 1 over 1 is very, very close to 1, so the answer will be 1. Same way if x is negative, so you'll see negative 100, for example. Then e to the negative 100 will become e to the 100, which is very large. So the whole thing will become 1 plus 1 over e to the 100, which is denominator is very large. So 1 divided by a large number is close to 0. So it will become 0, right? So you can think of the sigmoid as constraining the output. So f of x is the output. So output, as you can see, can only vary between 0 to 1. Okay. So it will help stabilize the learning process. It doesn't matter how many layers we are using. It will make sure that, at least it never explodes to a very high value. Okay. So that is one of the purposes of the activation function, right? In addition to constraining the output, we also want the neural network to learn nonlinear decision boundaries. Okay, so for example, let's say you are given some data, okay, and the data looks like there are some x's. Let's pretend it's two-dimensional data. Okay, and O's. Okay, so the goal is given an unknown point. Okay, so suppose this is our training data. So some XY coordinate for each point is given. And if it is in the region of the where you see X's, our neural network should classify as belonging to the X category. If the unknown point is somewhere over here, it should indicate it belongs to the O category, right? Which means our neural network needs to learn the separation boundary between the region of the X's and region of the O's. So if you take a look at in this example, the decision boundary is pretty, it's not a straight line. So it is sort of like this, okay? So because it's not a straight line, this is what we call the nonlinear decision boundary. Okay. So if you create a neural network, okay, suppose you create a neural network with a single neuron in it. Okay. It doesn't matter what activation function you use. Okay. You train it for different data or this data, whatever you look like, right? What you will discover is single neuron can only learn a linear decision boundary. It is incapable of learning a curvature. Okay. So this is a proven fact, and you will experiment it also in one of the assignments that I'll be giving you later on, and you'll see. So what that means is, even if you try to make it learn this training data that I showed you over here, right? The best it can do is it can come up with a straight line, something like this, where, as you can see, some of the X's will be wrongly classified, some of the O's will be wrongly classified, right? Because it can only learn a straight line, nothing else, okay? So that's why we use more than one neuron, okay? Now let's pretend we use, let's say, 5 neurons, okay? However, in these 5 neurons, let's pretend the activation function is a linear activation function. Okay, just like we were discussing, you know, where the activation function basically doesn't do anything. Input is 1, it passes it straight through, right? So what you will recognize is if we use linear activation function, then again, it cannot learn a nonlinear decision boundary, okay? So this also cannot learn a nonlinear decision boundary. And you can actually very easily see it. Okay, you can very easily see why that is the case. Okay, for example, let's take a look at a single neuron. Okay, with 2 inputs, X0, X1, W0, W1, and bias. Okay, assume this is a linear activation, right? So what is the equation for S? W0, X0 plus W1, X1, right? And plus B. Okay, if you remember from your basic math, if I give you y equal to 2x plus 3, what type of equation does it create? a straight line, right? It will be 3 with a slope of 2. The y-intercept will be 3, right? Similarly, if you have a 3-dimensional, or if I put 2 variables, 2x0 minus 3x1 plus 5, okay? So pretend now this is 3-dimensional data. X0 is one dimension, x1 is another dimension. So again, what it will do is it will create sort of like what we call a plane. Okay, but it will be like a flat sheet of flat sheet, right? Similarly, what if you put this goes to another neuron? Remember, all it's doing is multiplying it by another weight. So even if I multiply by another number, it's still, in terms of the inputs, it's still a linear equation. So even if we put a lot of parameters over, a lot of weights over here, a lot of inputs over here, all it's doing is creating a flat sheet in a higher dimensional space. Okay, so to summarize, what I'm trying to say is, if we use linear activation function, all it's doing is learning a straight line or a straight plane, a flat plane, whether it's in 1 dimension or 2 dimensions or 100 dimensions, it doesn't matter. It does not have the capability to learn something complicated like a curve or like a nonlinear hyperplane in high dimensions. Okay, so this is where we need some complex activation functions like sigmoid. You can see, you know, it has a curvature over here. So as we apply a sigmoid type of activation function, now you will see, oh, it is able to learn, you know, depending upon how many neurons we use, a nonlinear decision boundary. Okay. So the question is, how will our learning equations change? So coming back to our simple 3-neuron example, if this activation function is no longer a linear function, it's a sigmoid. Now, as you can see, previously, remember I was saying we will do partial L over partial A2, then partial A2 over S2. If it is a linear activation function, what was partial A2 over partial S2? 1. But now if I say it is 1 over 1 plus e to the minus x is the equation over here, can I still say it as 1? No. Okay, so what is that value? Okay, so let me quickly show it to you. Okay, so if the, oops. Okay, so if the activation function is becoming a sigmoid, so if this is a, this is S, this is A. So the question is, what is partial A over partial S if the equation for the activation function is 1 over 1, right? So let me quickly show it to you. So suppose y equal to 1 over 1 plus e to the minus x, right? Okay, from your basic derivative math, you will remember there's a numerator, there's a denominator. So you will treat it as if it's u divided by b, right? So remember, in this case, dy over dx will be, so I'm treating now completely math problem. So don't think of y as the target. Y is just the output, x is the input. So dy over dx will be given, if you remember from basic math, when you have numerator divided by denominator, is v du minus u dv over v squared. So If you haven't done calculus, don't worry about it. The final answer is very straightforward, as you will see. Okay, so let's plug in over here. What is V? V is 1 plus e to the minus x, right? What is U? U is 1. See, U is 1, and V is the bottom part, which is 1 plus e to the minus x, right? So what is derivative of U? What is derivative of 1? 0. It's a constant, right? Constant does not change. So now let's go to U. What is U? 1. What is dV? Okay, dV is the derivative of this 1 plus e to the minus x. What's derivative of 1? 0. Plus, what is derivative of e to the minus x? Some of you might recall it is minus e to the minus x. E to the x is e to the x, but e to the minus x is minus e to the minus x, right? Divided by v squared. So this will be, you guys agree? So if I write it like this further, 0 multiplied by this is 0, right? 1 times 0 is 0. So as you can see, this reduces to minus e to the minus x over 1 plus e to the minus x squared is dy over dx, right? Everybody agrees? Okay, so now let me show you, this can be rewritten. If I do y times 1 minus y, I'll get the same answer as this one, okay? Y is 1 over 1 plus e to the minus x multiplied by 1 minus y, 1 over 1 plus e to the minus x, okay? So if I expand this out, this will become 1 plus e to the minus x. And this one, as you can see, will become minus e to the minus x, because over here, think of it as 1. At the bottom, I will get 1 plus e to the minus x, right? So then this will become, this will become, this will become plus e to the minus x, okay? So if I, did I make a mistake? 1 plus,
Yes, sir. Here you used plus
1
after
plus
derivation.
x minus 1. Somehow I'm getting a one sign is not coming out correctly. Where did I make a mistake?
Yeah, in the first step, you use plus in between VDU and UDV. The derivative.
Left side
1
or
plus
the
e
right
power
side?
minus x into 0 plus you use plus. Here we get minus.
Okay, which part are you referring to?
1 plus e power minus x into 0
On the
plus.
right side or the left side?
Yeah, on the right side,
On
the second line.
See, this will be 0, right?
Yeah, the next part you
And
use plus here, but it's minus.
okay. That's right. This should be minus. Yeah. Thank you. So yeah. So if this is minus, then this becomes plus. Okay. So anyway, so then you will see the left side is. Okay. So now you will see this part is exactly same as this part. So in other words, dy over dx can be written as y times 1 minus y. Okay. So coming back to our neural network, what I'm trying to say is or let me redraw it again. So what I'm trying to say is, if this is sum, this is A, okay, then partial A over partial S is same as A times 1 minus A. You know, just like I said, if this input is X, output is Y, then dy over dx, just like I showed you, is same as y times 1 minus y, right? So in our case, the input is S, it's not X. Output is A, not Y. So if we have to determine partial A over partial S, and F happens to be 1 over 1 plus c to the minus x, then it is A times 1 minus A. So it becomes very easy to calculate. So in other words, what I'm trying to say is, okay, let's say at some point in time, A happens to be, let's say, 2. Okay, suppose it's 2. So what is then partial A over partial S? Okay, it will be 2 times 1 minus 2, which is minus 2. Okay, so it's very easy to calculate. So once again, let me go back again, just in case there was a tiny bit of confusion. Okay, so let me clarify it one more time. Okay, this is the equation for the sigmoid, right? So now we are sidetracking and totally treating it like a math. Equation is y equal to 1 plus c to the minus x. To find dy over dx, we can treat it as u divided by v. Okay. In math, if you are given a numerator and a derivative and a denominator, and you have to find dy over dx, this is the formula: v du minus u dv over v squared. Okay. So as we plug in, u is 1 in our example, is the numerator, v is the denominator, which is 1 plus e to the minus x. So v 1 plus e to the minus x, du is the derivative of 1, which is 0. So this part cancels out. Okay. Then if we go to u is 1. If we take a look at dv, which is this, so which is minus e to the minus x, right? Now we already had a minus over here, so minus minus becomes plus. So the v squared at the bottom, it will be v is 1 plus e to the minus x, so it's 1 plus e to the minus x squared. So dy over dx turns out to be this. Okay, so then what I said is, this is in reality same as if we did y times 1 minus y. Okay, because y is 1 over 1 plus e to the minus x. 1 minus y will become 1 minus 1 over, right? And if you do a simple addition of these, you will see this will become 1 plus e to the minus x minus 1 divided by 1 plus e to the minus x. Just this part. Okay, 1 cancels. So it is e to the minus x over 1 plus e to the minus x. And then now if we multiply it over here, it becomes like this. So you can see y times 1 to the minus y is same as dy over dx. Okay, so in other words, if you have an f, input is s, output is a, then partial a over partial s, just like we said, is y times 1 minus y. Y was the output before. Now a is the output, so it will become a times 1 minus a. Okay. So now let's go to a 3-neuron example. Okay, so suppose you have okay, suppose we have x0, x1, w0, w1, w2, w3, right? This is S0, S1. W4, W5, 1B2, 1B0, 1B1, A2, S2, loss Y and L. Okay, and L is 0.5 Y minus A squared, A2 square, right? Okay, so just like before, remember from now on, we'll be using the delta rule. So this supposes delta 2. This supposes delta 0. This supposes delta 1. Okay, so let's calculate all of these. Delta 2 by definition is what? Partial L over. Remember, it's the derivative from loss up to the middle of the neuron. So it is, everybody agrees? Okay, partial S2. So which will be, now how many parts are involved? Right? So which will be partial L over partial A2 times partial A2 over. Everybody agrees? So what is partial L over partial A2? Yes? Now can you tell me what is partial A2 over partial S2 if this is a sigmoid?
A2 into 1 minus A2.
A2 into 1 minus A2, excellent. So see, previously this was treated as 1, previously with the linear activation function. So you can see this gets added, okay? So now let's see what is the relationship between delta 0 and delta 2. So previously, what was the relationship? Previously, delta 0 was, what is the weight connecting these two? W4. So previously it was W4 times
4A delta 2.
Delta 2, okay? But remember, now we further have one more derivative involved from, if this is A0, partial A0 over, so it will further be partial A0 over partial S0 will get further, get involved over here. So what is the value of that? So
A0 into 1 minus A0.
A0 into 1 minus A0, yes. So that is the change from now on that will occur if the activation function is nonlinear, okay, meaning a sigmoid, okay. So let me see if you guys followed it. Can you tell me, let's go to our bigger picture, okay. Let's take a look at, how about we take a look at, all right, let's try to compute delta 1. Okay, so in this equation, sorry, in this 5 neuron example, suppose I ask you, give me the equation for delta 1 if the activation function is sigmoid. Okay, so how is delta? So again, easy way to remember is if the activation function was linear, right? So take a look, delta 1 is getting contribution from which other 2 neurons? the delta 2 neuron and the delta 3 neuron. So if I write the contribution for delta 2 neuron, assuming the activation function is linear, right? So it will be delta 2 times what? W5. Okay. Plus, take a look at the contribution coming up to this point from delta 3. So will be delta 3 times W7, right? So now we are okay up to this point, this thing, this dark circle that I'm drawing. Okay. Now to get to delta 1, we need further derivative from here to here. Okay. So this whole thing will be multiplied by what? Very good. A1 times. Oops. Got moved over here. A1 times 1 minus A1. Right? So you're not multiplying A1 times 1 minus A1 to W5 to W7. Just add these two together first, then, because like I said, from the picture, you can easily see it has accumulated the contribution of delta 2 and delta 3 up to this point, which is, scaled by W5, scaled by W7. So now all we need to do is go backwards to further multiply the chain of derivatives, which is simply A1 over S1, partial A1 over S1. If it is sigmoid, then that is the extra part that gets added, right? Okay, let me ask you one more question. Partial L over partial W1. What will be the equation over here? Okay, X1 is tied to sorry, W1 is up over here, right? W1 is only connected to delta 0. Okay, so it will be delta 0 times what? Times X1, very good. Is there further 1 times 1 minus a 0 or no? No, that's already included in delta 0. So that's it. Okay. So anyway, adding activation functions, you'll see the calculation of deltas will be affected, but not the calculation of the partial L over partial W's. Okay. So just 1 more minute, then I'll stop. Okay, so now you will get your second assignment where you'll be programming the 3 neuron, 5 neuron, and seeing how it works, right? Okay, so just like we discussed, sigmoid is one of the activation functions, 1 over 1 plus e to the minus x, right? And the equation is like at 0.5. So it constrains the output between 0 to 1. Okay, similarly, there's a tan hyperbolic is another activation function. And what it does, it constrains the output between -1 to 1. Okay, so the equation for the tan hyperbolic looks like this. It passes from 0. So -1 to 1. The actual formula, I forgot, it is something like, again, I may be slightly off. You can Google it, and it's something like this. But like I said, you'll Google it and find the exact equation. And also from derivative point of view, let me see if I can If I remember correctly, the derivative of the like partial A over partial S, if it is tan hyperbolic, it comes out to, if I remember correctly, something like 1 minus A squared. So instead of A, 1 minus A, again, based on my memory, but you will Google it, confirm whether, I was right or wrong. So in the assignment, what I will do is I will also give you your own enhancement that what if we replace sigmoid to tan hyperbolic? So I won't give you the solution, but you will go and program it and see how it works, right? So what we learned today, in case it was something confusing, go back, watch the video. But if it made sense, then like I said, this is the foundation of learning what we discussed today. The entire theory of neural networks, no matter how complicated they are, is based on the simple gradient descent algorithm where we learn to minimize the loss, okay? And we go backwards until we get to what we are looking for. Then we incrementally update the weights and biases until it has learned, okay? So then obviously there's a lot to learn, but the foundation point of view, what we learned today is the most important for your next steps, okay? So make sure you're very good at it, because if the foundation is not strong, we'll have problems later on. So anyway, look for a good assignment and we'll go from here.